Hello, everyone, and welcome to reInvent. My name is Sandeep Kulkarni, and I am a chief architect at Amazon Web Services, predominantly focused on the automotive vertical. Joining me today is Mahadevan Krishnan, who leads architecture at Toyota Connected, and I'm really excited to share the stage with him today. We've got a big agenda, so let's jump right into it. We want you to walk away with an understanding of how Toyota Connected is leveraging Amazon Web Services and the cloud to transform themselves from an automotive business into a mobility services business. In the first part, Mahadev will talk about Toyota Connected's vision, the challenges they faced, and the significant outcomes that have already been accomplished over the last year. Then, I will deep dive into the architecture and also discuss an interesting software engineering challenge that we faced and solved. Finally, we will provide you with a peek into what the future looks like. It is my absolute pleasure to welcome Mahadevan from Toyota Connected, who will take us through the first part of the agenda. And I'll turn the mic over to him.
Thanks, Sandeep. About 2 years ago, our president, Akio Toyoda, announced to the world that we will begin transforming Toyota from an automobile company to a mobility company. To do that, we have been focusing on four primary areas: connected, autonomous, shared, and electric. The world of automotive has been constantly changing. In the past, companies made cars. They sold these cars to customers in the traditional retail process, creating one-to-one relationship with customers, and the car created value for them. But today, companies are offering mobility services in new ways, and this starts to redefine the value for our customers. Lots of things have changed over the years, but the customer expectation remains unchanged. Value must exceed the price, and experience must exceed the friction of use. The future world of mobility is undefined and unformed. We have an amazing opportunity in front of us to define the future of mobility for new generations and for future of Toyota. To go where others have not been and to deliver memorable customer mobility experiences that will define the future of mobility. Toyota Connected is leading this transformation of Toyota's transition from an automotive to a mobility company. We use technology to transform how people interact with their vehicles, provide predictive and contextual services that anticipate our drivers' needs. So, how is Toyota Connected working on achieving this mission? We have been focusing on four key pillars: customer experience. In-house research and design capability is central to our shift in terms of becoming a digitally minded, customer-centric design-led force in the world of automotive and mobility. Platform and enabling technologies. Our connected ecosystem combines best-in-class partner capabilities and in-house expertise to create a scalable solution that enables fast go-to-market with localizable and customizable customer experiences. Safety and security offer robust and contextualized data services that make driving and transportation safe and secure. Focusing on safety and security will further support Toyota's position as a leader in future of mobility, automotive and beyond. Convenience and access. Remove the friction and pain of everyday in and out of vehicle experiences. Doing so help us make connected life a more human experience. Toyota's connected vehicles have hundreds of sensors under the hood that streams data in near real time from the vehicles. That translates to millions of data points collected from the connected vehicles per day globally. This helps us in understanding various things such as whether the window is open, how fast the car is being driven, what is the mileage, what is the steering angle, where is the car located. But all of this we do only with the consent of a customer. The data is being collected in order to drive two primary use cases. First, building data services for our customers that really drive customer satisfaction and give customer the new capabilities around safety and convenience. And second, take the insights from this data and start improving the products. We do not collect the data until customer understands what data is being collected and how it is being used. Customer has an option to opt out at any given time. Our engineers use data to make every experience in Toyota vehicle personal and memorable for our customers, but not creepy. We proactively embed privacy into the design of each one of our products and service that we build. And now comes the question, how do you take all these millions of data points that are binary, encoded, and convert them into a valuable information for our customers across the globe and make it available to them in a form factor of their choice? One example is that the data points collected could be used to generate a driver score that lets a person to understand how well they are driving and deliver that score to their own mobile device when requested. A second example is that data points collected could be used to provide real-time telemetry information for their fleet of vehicles to the rental car companies so that they can use it for tracking fuel level, calculating cost, or for any scheduling purposes, which will enhance their customers' experience by eliminating the wait times at the rental car companies. We are building a scalable global platform, and our customers in various regions around the globe can access their data locally that improves safety, enhances convenience, and enables mobility for millions of Toyota vehicle owners worldwide. Building such a global platform at scale will always come with challenges. We will talk about the challenges that we faced during this journey, the options that we considered, and what actions were taken in order to overcome these challenges and enhance the customer experience. As we were building this mobility platform, three key challenges were ahead of us. Scalability. Platform should be highly scalable given that it is a single platform supporting more regions across the globe. We need to ensure that the application has always the right amount of capacity to handle global traffic demands, as system cannot afford any downtime as we are processing the messages coming off of the vehicle's sensor in real time. Resilient. Given the nature of system being real time, it should be fault tolerant and it should be able to detect whenever the system is unhealthy, terminate them, and launch an instance to replace it either in the same availability zone or different zones depending on the zone which becomes unavailable. Platform should be cost optimized. Platform should be able to increase or decrease the capacity as needed so that you can save money and terminate them when they are not. Given the need for single platform to support multiple regions, it was necessary for us to see how we can go back and optimize the platforms. Costs were slowly getting out of control, and when we started doing the deep dive, we quickly realized that a lot of costs were around storage and transmission. A lot of data that were getting sent from the vehicle were actually not needed. For instance, whenever the vehicle transmits the data from sensors like door sensors, it will transmit 1 for door being open and 0 for door being closed. It was simple, but you can imagine the volume of these data when it is being collected across millions of vehicles, and it easily escalates the cost. We started wondering if there is any value in terms of capturing the near constant values, given that it will just keep transmitting zeros while the car is in transit. Leaders on the engineering side gave us a clear mandate that every message transmitted from a vehicle should have a purpose, provide quantifiable customer value, and be processed if and only when it is needed. Hence, we decided to go back and configure the vehicle to transmit data only when there is a change in near constant values. This helped us in saving costs significantly on the storage and transmission, but still, compute was always a challenge. But with AWS, we have multiple options for compute. As we built the platform initially, it was able to scale well, but it turned out to be super expensive in a very short time. We started exploring what if we went ahead and moved platform into a reserved instances that provides discount of about 72% compared to on-demand pricing, which is great. But the challenge is that you must make a commitment for up to 3 years, and we were not ready to make that commitment yet until the platform matures. Then we started thinking about spot instances that can provide cost benefits without any fixed commitments. But the downside there was that it can be interrupted anytime as it is just a spare capacity available within AWS infrastructure, and they may not be there when you actually need them. We decided to use them for analytic workloads that can be run at a time when you have enough computing capacity available, or tasks that need some extra computing capacity to enhance the performance given the volume of data that is being processed. Spot instances may not be ideal for real-time services like location services, which were critical for mobility. Finally, we settled on serverless. As we started on this journey, we realized that serverless is what we were looking for, as it provided us with the increased agility, flexibility for scaling, and lower total cost of ownership. This resonated well with us, the famous just-in-time Toyota production system that inspired lean manufacturing in US, which states make what is needed only when it is needed and only in the amount that is needed. Mobility Services platform was built to cater to both retail and fleet customers. Most of the fleet companies do not just have Toyotas in their fleet. They have vehicles from Audi, Nissan, and Ford in addition to Toyota vehicles in their fleet mix. Fleet companies were apprehensive when we started saying, hey, come into our platform, which is a closed platform. Fleet companies were excited to use the mobility services product launched by Toyota, but at the same time, they wanted to get these services embedded into their platform rather than coming into a closed platform which is developed by Toyota. We understood that we are not purely looking at Toyota's customer anymore who wanted to make use of these mobility services, and rather, we are looking at providing seamless experience to customers of the fleet companies who are used to fleet companies' app experience. The message was loud and clear that we needed an open system because we were not looking at just the B2B and the B2C relationships here, and we were slowly getting into B2B2C. Customer want their technology anywhere and everywhere. So whether it's a car rental company that is providing connected mobility services to their customers, or maybe it could be a hotel that a Toyota dealership is partnering with to leave their cars in the garage so that the customers can use those vehicles, that enhances the vacation experience. And this made us think that and reimagine our mobility services platform to be of more open platform. Platform really starts with Toyota vehicle and vehicle technology, which is the core. Around this, we have a communication device, data, access, and multimedia. They are all part of Toyota vehicle. Toyota Connected now takes the API management and data collected off of the vehicles with the available access and creates services for managing devices and safety and other data services in the form of APIs for getting location, tire pressure, odometer, and fuel, and access services like remote access and digital key, and multimedia services for linking mobility applications, along with the consent and the API management. Finally, all of this is brought together under our mobility marketplace portal that uses subscription services to make sure services are consented to and are being provisioned correctly. We provide the option to customers to pick and choose the services that deliver value to them. Now I will hand over to Sandeep, who will walk you through the architecture of platform.
Thanks, Mahadevan. That is a wonderful depiction of reimagining mobility exposed through Toyota's APIs and microservices. Now, let's dive deeper into the design and architecture. Given the growth projections of millions of vehicles, each capable of transmitting billions of data points, the first order of the day was to come up with a robust data lake architecture. We settled on the serverless pattern, which provides scalability, resiliency, as well as opportunities for cost optimization. The pipeline is broken into 4 parts. The first part in the ingest block is ingesting data from millions of connected vehicles into the serverless Kinesis data streams, processing the data through serverless Lambda, and first landing it into the raw S3 storage bucket. The second phase, this is where the decode Lambda function does most of the heavy lifting and converts the data from its encoded encrypted format into a JSON format and writes that data to the decoded S3 bucket. Then we have the transformation jobs that enrich the decoded messages and transforms them into Parquet format so that it is now set up for analytics purposes where we have data available by vehicles as well as by different models that the data scientists can query using tools like Athena. The real-time pipeline also sends these decoded messages to downstream services by populating them in Dynamo and then exposing those through APIs so that services like telemetry, driver score, event notification, etc. uh, can consume these services. Now let's tie this back to the three challenges that Maha talked about. The serverless pattern is inherently scalable. Kinesis data streams are scalable by simply increasing the number of shards that are there in the data stream. The Lambda functions scale with the Kinesis shards. Firehose is inherently scalable, and S3 has infinite capacity. And this is the core foundation of our data lake. The resiliency comes from the fact that this can be deployed into multiple availability zones. AWS does some of the heavy lifting, like deploying Kinesis data streams, Firehose across 3 availability zones, while we have placed our Lambdas also into multiple availability zones to give us the resiliency that we're looking for. The Dynamo tables are replicated across regions, giving us an even higher level of resiliency. We have definitely put to use the cost levers that have been given to us by Amazon. We heavily use Spot instances for the EMR jobs that are used during transformation, which can provide up to 70-80% savings. Serverless means that we only pay for what we consume, and both S3 and Dynamo give us the opportunity to store the data only for as long as it is required. In S3, we store it in the hot storage for the duration, and in Dynamo, we again store it in the tables, but we set the time to live flag so that the data, once it is stale, is automatically discarded. The range of mobility services that has been developed by Toyota is broad, and now let's take a look at a couple of examples so you understand what these services are used for. If you are a dealer or a fleet management company and you want to ensure that your employees are driving at reasonable speeds in a parking lot, you can set up overspeeding notifications on the cars in your parking lot so that you are notified if anyone in the parking lot is driving over, say, 10 miles an hour. Another use case is about the service warning. Rental car agencies are focused on achieving the highest levels of customer satisfaction, and they want to ensure that their drivers have the best possible experience with the rented vehicles and avoid any unpleasant breakdowns during the course of the rental. The service warning capabilities from the vehicles will alert you to any proactive maintenance that you should complete to ensure that the vehicles continue to operate smoothly. And then there is a wonderful case about geofence notifications. Rental car companies may want to put restrictions on driving the cars in the United States. And if they have those restrictions, then for drivers in Texas or California that cross the border, they may want to receive notifications for those incidents. And with the geofence notifications, if you set a geofence around the United States, then anybody that's leaving the country and crossing the border, you would get those notifications. So here you see just a sampling of the different mobility services that have been developed by Toyota, but there is several other services that have both been developed as well as in the making. Now we're going to switch gears to an interesting software engineering challenge. And this challenge is centered around what we refer to as micro collisions. Well, what is a micro collision? A micro collision is like a minor bump or a fender bender that typically falls below the threshold of an airbag deployment. Why do rental car companies care about micro collisions? Well, the fact of the matter is that these cars now have the potential to be rented multiple times during the day, sometimes for just an hour or two each. And there may be situations where, when a person is renting the car for an hour or so, could cause a minor bump and not report it. And then that bump gets detected later, after a day or two. Well, if it is detected after a day or two, then it becomes difficult to pinpoint who exactly was responsible for the damage. And since the damage affects the residual value of the vehicle, you want to know who you should assign the responsibility for. Now, why is this a difficult problem to solve? Well, it's a difficult problem for multiple reasons. The first is that you are dealing with a large amount of data. That's, millions of vehicles and billions of data points. And that itself can get you overwhelmed. The second reason is that while you have an enormous amount of data that is used to detect these collisions, the data in the pipeline is sparse, it is disjointed, and it's not available in a single upstream package. A wonderful analogy to describe this is like picking up specific water droplets from a fire hose that is set wide open. Think about how difficult that is. That is exactly what we're trying to accomplish here. And the third reason is that while we want to capture collisions at all speeds, we also want to ensure that we are eliminating false positives like harsh braking or harsh cornering and or going over potholes. So we started this journey. We said, well, let's take a look at what we have. And the first thing that we defaulted to was, hey, we have the data lake that we have been built. We have Athena, we have EMR. Perhaps we could just write large queries to link the sparse and the disjointed data points together to determine the collision. But we realized that this means that you have to go back and reprocess the data after the fact. The queries are large, therefore time consuming and costly, and they're not providing real time value because we are doing this after the fact. So we said, well, why not try a variant of this option, which is maybe we will store the relevant data sets in a database like a Dynamo database and have it indexed correctly. The advantage of having data in database is that we can query the data much more efficiently. However, even in this use case, we realize that we have to do frequent lookups to piece the data together to extract enough data and detect a collision for one vehicle. And then we would have to repeat the process for every vehicle on the road. While this could scale from a technology perspective at Dynamo, it simply would not scale from a financial perspective. And so we decided to also abandon this option. So then we thought, hey, why are we trying to reprocess all this data after the fact? Why not use the ingest pipeline, which is the real-time pipeline, which has already been scaled, and perhaps we can put that to good use, and therefore we built upon that pipeline. What you see in this picture is that we have the data coming into the Kinesis stream, and in step 2, we have a Lambda function which acts as a filter. This filter basically takes a look at the data and evaluates the values for acceleration, velocity, and displacement and determines if they exceed certain thresholds. And if they do exceed the thresholds, then we put them onto a queue. And in this case, we're using the SQS functionality, and we specifically need the delayed visibility feature within SQS. Well, why do we need this delayed visibility feature? The reason why we need this is that the collision event is actually happening over a span of a few seconds. So what we need is the ability to go back in time, let's say 60 seconds back to when we first detected it, and then perhaps 60 seconds later to get enough of a sampling, about 120 seconds, that we can then analyze. So after the messages that were put in the SQS queue are visible, they go through the rest of the pipeline and we come to the Lambda function in step 7, which does the heavy lifting. So this Lambda function goes back to the original Kinesis stream and picks out those data points of interest for that particular win, packages them into a single packet, sends it off to a supervised learning model that is hosted in EKS, and if the model returns that there was a collision, then we capture the data points in a DynamoDB database, and we also issue a notification through SNS. This approach actually worked really well. It's a near real-time solution, and at lower volumes when we did the benchmarks, it scaled very well. However, when we decided to run a benchmark to test whether it could scale to millions of vehicles, we saw occasions where we were getting throughput exceptions from the Kinesis data streams. And we realized that we were putting more load on the Kinesis streams as a result of the Lambda function in step 7 going back and reading data from Kinesis. It was exceeding the Kinesis limit of 5 requests per second per shard. Well, how do we solve this Kinesis scaling issue? One approach was that we could have just increased the number of shards to provide more throughput, but then that would have turned out to be a costly solution. So instead, we decided to introduce a cache, which is the Elasticache, a Redis Elasticache. And the logic is the same. The candidate filter Lambda function in step 2 evaluates the messages. If they exceed the thresholds, not only does it put this message onto the delayed SQS but it also puts it into the cache. And it also puts subsequent messages for that win into the cache. And you proceed through the pipeline, and again, when you come to step 7, the heavy-duty Lambda function over here, now instead of going back and trying to retrieve those messages from the Kinesis stream, is actually retrieving this from the Elasticache, which is really, really fast. So this approach, when we benchmarked it, scaled beautifully to millions of vehicles that we were benchmarking this against. And it was also a real-time solution. So why did we choose Redis specifically? Well, there's multiple reasons why we chose Redis, and some of them have to do with scalability. It allowed a dynamic way for us to add or remove shards, and we could further partition the data by shards, allowing for quick lookup. The APIs that are provided by Redis are simple yet rich. So through a simple API like zadd, you can quickly add an element to a sorted list. We also set all the elements to expire after 20 minutes, following the principle of, hey, does the data have any value at this time? And also, other APIs like zrange by score allowed us to quickly retrieve data points in a range between min and max, which would give us the specific disjointed data points that we were needing for further analysis with the supervised learning model. Hopefully, what this example tells you is that architectures evolve. It's an iterative process. You go through it till you arrive at the architecture that works best for your situation. Finally, a peek into the future. What an incredible journey for Toyota Connected. Back in 2018, we were leveraging about a half a dozen AWS services to build the foundation. In 2019, we expanded our suite of services and started serving APIs, and the volume quickly reached the billion transactions per month mark. Fast forward to 2020, we're now using 3 times more AWS services. We're exposing many additional APIs. The traffic has grown 18-fold. We are now serving 18 billion transactions per month. And as we look further into the future, we will be leveraging additional services from AWS. Specifically around edge computing, we think Greengrass has great potential. We are looking at lake formation to simplify the data lake administration. We fully expect that the traffic will continue to ramp up, and we will serve more APIs. It's simply remarkable to see how well AWS has scaled to meet Toyota's needs seamlessly, from hundreds of thousands of vehicles when we started to millions of vehicles now. This has been an excellent partnership with Mahadevan and the entire team at Toyota Connected, and we have very much enjoyed and learned from this experience. Thank you for your time. And we also have a session survey, and we would encourage you to please fill out the session survey and give us feedback. Thanks, and have a wonderful day.